This week our speaker is Erin Nissen. Erin is a junior chemistry major, physics minor. I like to think in another life she may have been the reverse, physics major, chemistry minor, but unfortunately for us, she went with her first love, which is in fact chemistry. This summer, she did an REU program at University College, Wellesley College in Massachusetts. And she's going to tell us all about her work this summer. After she graduates, she's planning on going on to graduate school, and I'm assuming something to do with organic chemistry or something like that. So anyway, without any further ado, let's welcome our speaker for today.
All right, thank you all for coming today. So, like Middleton just told you, my name is Erin Nissen, and I'm a junior, and I went to Wellesley this summer and did organic research that has to do with trying to come up with a better technique for diabetes treatments. And it was an REU program, so I went and I did research all summer long, and it was awesome and amazing, and I'm hoping to continue do another one this summer. So, but before I get started, I just wanted to kind of maybe say why you should care or listen. So this is my example, is at Harvard, there's an astromedical medicine project, and it just comes to show that like medicine, like a PhD that's a doctor, went to an astrophysics or an astronomy talk and was like, that's so cool, I should take that and apply it to medicine. So you never know by listening to a different talk and a different subject, whether it be physics or geology, what you could learn and apply that to what you're studying and make it applicable to what you're interested in your field. So I always think it's important to go and listen to other seminars from other sciences. So to start out, I thought we should also talk about a little bit of terminology so that you're not confused when I refer to these things. So up here at the top, we have a carbon framework. So we don't always draw all out our carbons and our hydrogens because we're lazy and that's too much work. We draw out this nice hexagon framework, and that's just assumed that those are carbons at the points and that there's hydrogens coming off of them. I also wanted to tell you all that there is this is a picture of the glucagon-like peptide 1 receptor, which is what has to do with diabetes. And a receptor is just something that a molecule comes and I'm going to give you guys my version of a receptor. The molecule comes and tells the receptor to turn on, and then it goes on in its cascade of events to help with the insulin in the body. And insulin has to do with the glucose, the blood glucose level, so regulating that blood glucose level so that you can work properly and be a healthy human being. So everything has to refer back to this GLP-1R, the glucagon-like peptide 1 receptor, working properly in your body. And so I also wanted to talk about this depiction, which will come up a lot later in my presentation. So every time you see an arrow pointing at something, that means that there's electron movement. So electron density is being moved from one atom to another one. The lines between the bonds is just a covalent bond, so that means those things are actually attached to each other. And charges for this presentation, we're going to consider them bad. Charges are bad, especially if they're on carbon. We don't want charges to be on carbon. So for type 2 diabetes, there's a resistance to insulin. And so there's a problem with the GLP-1 receptor that I just talked about in my last slide. So they found this molecule, GLP, glucagon-like peptide, really similar in names, I know, that has a half-life of 2.5 minutes in the body. And what that actually does is it helps fix that receptor's problem, and it helps with the problem of type 2 diabetes. The only thing is it only has a half-life of 2.5 minutes. So that's not really something you would look for when trying to create a drug, because it's not going to last long enough in your body. So what we want to do is try to find a drug that can mimic this GLP-1 drug or molecule and turn on that receptor. So this Japanese pharmaceutical company came across this molecule called TO632. So TO632 can bind in similar places that the GLP-1 molecule does on that receptor in order to help with that cascade of events that releases insulin into your body. So if we can figure out where TO632 turns on that receptor, what amino acids it's binding to on that receptor, we can then create a molecule that we could use as a drug to help with diabetes treatments. That's like the overall goal, is to come up with something like these molecules for a drug. So I was working with Dr. David Haynes in the Haynes lab, and there were about 7 of us or so, and we were all working on creating this molecule, TO632. And every time you see a little star or an asterisk, that's where we were working on trying to iodinate this molecule. Now I'll talk about why we want to iodinate later, but the section, everybody had a different like ring that they were trying to put an iodine on, and they were either trying to selectively iodinate or put more than one iodine on TO632. And so I was trying to put an iodine on right in that top corner where the maroonish circle is, and only iodinate in that place selectively. So that is where my iodine would be. So you might be wondering, why put on an iodine? So we would want to put on an iodine so that we could then change the iodine to an azido TO632. TO6 is just the shorthand. Chop off those 2 numbers. And then once we turn it into an azido TO6, we can then blast it with UV light, and it'll turn into a nitrene. And that nitrene is very reactive, and it will covalently bond onto that receptor. We then send it to Mayo Clinic, and the Mayo Clinic chops up our TO632 bound to our receptor, and they can analyze those amino acids and figure out what's actually going on with this receptor. Because right now we don't really know what amino acids there are, so we can't produce the right type of drug. So what I started out with was everybody's favorite amino acid, phenylalanine. And the reason I started out with phenylalanine was because I wanted to iodinate selectively in the position right there, which we refer to as the para position, or number 4, if you count 1, 2, 3, 4. I also started out with phenylalanine because I wanted to work on ring closure techniques. So if you remember that molecule previously, there was a double ring formation. And so I wanted to work on closing up that nitrogen onto the rest of this hexagon 6-membered ring. So there it is. This was the goal project, was to get 7-iodoisoquinoline 3-carboxylic acid. And I wanted to iodinate before I attached to TO632. And the reason for that is because if you attach it before, the iodine actually goes to a different place on the molecule. And so then when you attach it onto the receptor, you don't really know what you're looking at. So it's really important that you actually know exactly where that iodine is on the molecule. I also wanted to iodinate before I close the ring because it actually won't go on the ring. If you try to iodinate with the ring closed, it just doesn't go on. It just stays as iodine. So this is a synthesis overview. This is what I worked on the whole summer. This is like my overview. So if you notice, we start with phenylalanine, and we take this carboxylic acid, that's what's over here at the top, and we take this OH group and we add an OCH3 onto that end. That's just for solubility reasons. You'll notice that at the very end, the very last step is to change back from this oxygen attached to a carbon attached to 3 hydrogens back onto that OH group. Then after I did that, I added an aldehyde. That's what this group is referred to, which is just a carbon double bonded to 2 oxygens, and we have a assumed hydrogen over here as well. Then after I added my aldehyde, I then iodinated because, remember, I wanted to iodinate before I closed my ring structure. After I iodinated, I wanted to close up my ring. And then not lastly, but then I wanted to form this double bond. And that is just a stabilizing, that just stabilizes the compound. There's a flow of electron density between these 2 rings when you have all of these rings with those double bond structures like that. Okay, so if you remember, that's the goal. That's the goal project, is TO632. And my portion was the marooned circled area. Okay, so before I show you a little bit more details of the synthesis, I wanted to go back over what the mechanism type things refer to. So an arrow is electron movement. So we're moving that electron density from atoms to atoms. The lines between the atoms are covalent bonds. So that means they're actually attached. And for the sake of this presentation, charges are bad. So if you see a charge on carbon, that would be something that is bad. And so then that leads me to my second picture that I have up here, is whenever we see this carbon double bonded to an oxygen, there's actually a resonance delocalization, which means those electrons are being distributed between the carbon and the oxygen. And they're actually residing on that oxygen, creating a charge on that carbon and the oxygen. And when those charges are there, that's why they would be susceptible to attack from a different atom. So the first thing we did was esterification. So you added an ester, and I started with thionyl chloride. That's this molecule up here with the sulfur and the chlorides, and I added methanol to it. And when I add that compound to phenylalanine, we then get the electron density movement of the oxygen coming on and attacking that CH3 and adding this OCH3 onto the end of phenylalanine. So then, I'm not going to go into all of the details of this one because it looks a little bit complicated. But what I do want to point out is that the top molecule is called EDCHCl, and that's the one with the 3 nitrogens. And then the one over here with the 6-membered ring and then the 5-membered ring with the 3 nitrogens is called HOBT. And those are 2 pretty expensive molecules. And we go through this reaction and we move our electron density around to end up with this end product with the aldehyde on the end, with the carbon double bonded to that oxygen. So we use these really big, bulky materials just to add on those 2 atoms, and a hydrogen, so to add on that aldehyde group. And then you also have to purify it. It's not very pure, and it's a really hard reaction, and you get a really low % yield. And so I was really frustrated with this reaction for a really long time. And so I decided to try something else because I thought it was a little ridiculous. And so I added ethyl formate to my phenylalanine, so my starting product. And we have our electron density movement with those arrows going on. And I came up with a mixture of 2 products. So ethyl formate is a lot cheaper of reagent to use, so that was a bonus. But I still ended up with this mixture of products. So that was kind of upsetting because I still would need to purify those 2 and separate them out. So then what I tried to do is add ethyl formate to my already OCH3 phenylalanine. So then I got exactly what I wanted out, and I didn't have to purify, so that was awesome. I was very excited that I no longer had to use this step, these very expensive starting materials, and I then could use just ethyl formate to add that aldehyde group onto my phenylalanine. So step 3 is iodination. So this is where I added my iodine onto my phenylalanine. And so we started with this compound called NIS. And NIS is very light sensitive, so this was kind of a fun one. I had to wrap my beaker or my round bottom flask in tinfoil, and all the lights had to be off when the reaction was running. And we used sulfuric acid also in this one. And as you can see, there's a lot of electron movement onto, which gives us a positive charge on that carbon right there. And that's bad, remember. So then the nitrogen then has to donate electron density to that carbon so that it can be happy. And then that nitrogen then has a positive charge, which once again still isn't good. And that's why the iodine is susceptible to attack and can add on to that ring in the para position. Okay, so before we talk about the ring closure techniques, which is what most of my research was over this summer, I just want to point out that basically all we're doing here is a dehydration reaction. So all I'm doing is I'm losing water. I'm losing a hydrogen from my ring. I'm losing a hydrogen from this nitrogen, and I'm losing that oxygen right there to lose water altogether. So in the first ring closure attempt, I started out with trifluoroacetic anhydride, And as you can see, there's a lot of movement with my electrons density. So we added on a carbonyl, that's what that carbon double bonded to an oxygen attached to a carbon with 3 fluorines onto that oxygen. And then we actually get a second attack of the trifluoric acetic anhydride with that double bond between the carbon and the nitrogen. And then that puts that positive charge on that carbon, which we said earlier was bad. So then the electron density from the ring can then come in and attack and make that positive charge go away and make that ring closure technique happen right there. We then add a little bit of water, and that water makes basically moves around the electron density to make that carbon double bonded to an oxygen and CF3 fall off of both of the ends of that carbon and nitrogen. But it didn't really go as well as planned, and there was it was very, very low yielding, and most of it was just starting material. I tried it in 2 different solvents to hopefully overcome that energy barrier that was going on, but it still didn't make enough of what I wanted. So, and there was also a lot of side products, a lot of really weird things going on in the flasks. So we moved on to attempt 2. So in attempt 2, I added hexamethyl disilazane, which I referred to as HMDS because that was quite the mouthful, and trifluoric acetic acid. And we add that hydrogen onto the nitrogen, which gives it a positive charge, which means that we need to make that positive charge go away and satisfy that nitrogen. And we do that by the electron density of that double bond between the carbon and the oxygen comes in and takes that sulfur off of the nitrogen. We then create this resonance delocalization between that double bond, that carbon and that nitrogen, so that positive charge. And to satisfy that positive charge, the electron density inside the ring is going to come on and close up that ring. However, it didn't really work that well, and it made pretty much exactly the same thing that the last one made, which I thought was kind of unique since I'm using HMDS in this one. But it made a lot of the same compounds, a lot of the same mass specs showed up in this machine that we use to determine the molecular weight. So then I moved on to attempt 3. So in attempt 3, I used this molecule called P2O5, which is a pretty cool molecule because it reacts with air, and so you have to keep it closed in its jar, and when you pull it out of the jar, you have to throw it in your reaction flask really fast, otherwise it'll start to create this really slimy goop, which is not what you want at all. So this one was kind of a hectic reaction, but it was fun. I liked it. Once again, you just have that same type of hopeful electron density movement throughout the ring to close that up. However, it pretty much just resulted in a black goop of not what I wanted. I'm not quite sure what it made, but it was not what I wanted. So I moved on to attempt 4. Now, attempt 4 is pretty cool because we end up with a 6-6-5 ring structure. And I started out with oxyl chloride, and once again, we're doing that same electron density movement. We're just trying to move around those electrons so that we can get a carbon deficiency with that positive charge, and then the electrons in the ring will come in and close that ring up. Now, once we close that ring up, we have parts of our oxyl chloride still hanging off of our ring. So then we add ferric chloride, and then we form our 6-6-5 ring structure with our double bonded oxygens coming off of that 5th ring structure, which then we can add sulfuric acid, and the sulfuric acid will help make those leave as leaving groups and leave us with our isoquinoline structure in the very end. So I have 2 structures drawn up here, and that's because one has that flow of electrons between both of the 6-membered rings, and one only is partially missing one of those double bonds. And so what happened was I was expecting the top one to happen, but I actually got out the bottom one, which is exciting because that's what I was going for in the end anyways. So then I took my bottom reaction, And I did a simple hydrolysis reaction, which just means that I add water to my, my product. And when I add water, I get this electron movement again, where I protonate that top oxygen, I add an H to it, and then we have that a positive charge on the carbon, and the oxygen comes in and it helps satisfy that positive charge on the carbon again. And then we end up switching from that OCH3 group to an OH group on the end. Now, this was great, it worked. However, it was very low yielding. It was a very, very low yield. And if you noticed, I went from step 4 to step 6. That was on purpose, because if I were to do this reaction again, I would add in a step 5 reaction. Because when I went back and read back through the literature, I found out that the paper that I was following was actually trying to create the product drawn in blue, whereas I got out the product in red by luck, just by luck. So if I added in a step that helped convert a lot more of the product that I got in blue over to the product that I got in red, then I would get a higher yield. And there just happens to be a reaction that does that. So if I were to go back through this, I would add in a step 5, and I would hope that that would increase the yield that I got out in the end for my isoquinoline. Okay, so if we want to go back over the benefits of this whole reaction, why we went through everything that we did. The whole main point is so that we can make this molecule TO632 and iodinate it so that we can turn it into a nitrene and then an azido and then attach it onto the receptor. And then once we attach it onto that receptor, we can then chop it up into little pieces and learn about the different amino acids that are on that receptor. And once we know about the amino acids that are on that receptor, we can then produce a better drug that would be more efficient at helping that receptor turn on and helping with diabetes treatments. Okay. And I would just like to thank the NSF REU grant for letting me come to Wellesley College. And I'd like to thank Colorado Mercy University and Dr. Richards for giving me my organic background, my friends and my family for supporting me, and of course the entire giant Haynes Lab for being very supportive and giving me a wonderful summer REU experience.
Questions?
Yes.
I got a question. As a physicist, I have no idea how all this stuff works in terms of, you talk about cutting this off in here, and obviously you're not using scissors. So could you just give a little bit about, like, when you do this, like obviously you're adding is it all done in some kind of solvent? Could you just give it a little bit of detail of like actually what you did and what you poured and all that stuff going on?
So I have a reaction. I have a round bottom flask, and I usually have a couple of solids or so. And you usually put your solids in first, and then my solid might be like phenylalanine is a solid, and then I add maybe like sulfuric acid, and that would be something that was reacting, and maybe I would put it in a solvent. Yes, so a solvent is something that the reaction is taking place in. So I would put all of these things in a solvent, and then I would heat them up so that they could overcome that energy barrier, because right now they're just stirring around in their flask. But once I heat them up, or maybe I cool them down, I do something to it, and then they can overcome that energy barrier and start reacting with each other and want to actually change form from this solid that was phenylalanine to a dark oil that was when I added like an aldehyde group onto it. So yeah, so all of these reactions are taking place in a reaction flask, and you add a bunch of things. Usually you heat them. I did a lot of heating. Or you are light sensitive and you cool things. A lot of times you have to put stuff in an ice bath, and then it will prevent something from happening or make the reaction happen faster. Does that answer your question?
Yeah, so the solvent, the things you add, the temperature, those all have an effect on which reaction is going to occur where and things
exactly,
like that.
Yeah. If you use a different solvent system, a different reaction might happen. or the reaction might not happen at all. Like one of them I changed from chloroform as my solvent to pyridine as my solvent. Those are just two different molecules in order to hopefully be able to get over the energy barrier to heat it higher. And it still didn't work, but it was an attempt. It was a try. Yes.
Then how do you know what you get when you're done?
There's lots of different processes. There's lots of different tests. Mostly what I used was this machine called a GCMS, and it tells you the molecular weight of whatever you've produced. So it tells you like fragments that have come off of that, and certain things can only fragment in certain ways. And so the fragments really identify what you've made. And so that's why I could tell that between two different reactions, I was making the same sort of thing because they were fragmenting in the same exact pattern. And they had an end mass of the same molecular weight, even though I was using completely different things in the reaction.
So actually, I have a question related to that, which is in the step 5, and we go back to that, is that okay? Well, either one of those. I mean, you got both of those 1 point, right?
But yes, we got both of those.
How do you tell the difference between those? I mean, it's just one bond, right?
Yes, you have to analyze. There's a machine called an NMR, and we put it in the NMR, and it gives off different peaks at different signals. Yes. And so it's very tricky at this point because you're right, there is only one difference, and there's a lot of overlap of a lot of those bonds show up in really similar areas. And you also can do different tests, like they might have different melting points, or they might move differently in a solvent. If I tested them on, like you have like a piece of paper, it's called a TLC, and you see how they move differently from each other. So you could really tell which one was which. There's also a fancy machine where you can do purification through, and it will read different bonds that are going on throughout the machine. So it'll, yeah. Yes.
One of your original slides, there were a number of asterisks that showed
Yes.
different iodination sites.
Mm-hmm.
Do those all bind to different spots on the receptor so you get different amino acids from?
Yes, so the thing is we don't know exactly where they would bind. That's what we're trying to figure out. And so by putting the iodine on in those different places, we then can maybe learn more places or more amino acids that are on that receptor because we don't know where they're binding. It would be a lot better if they did bind in different places because then we could learn more, but we don't know exactly where they're binding at the moment. Yes.
So I'm curious, so each step of the process, I mean, is it a similar time delay? I mean, how long do these things, again, as someone who's ignorant in chemistry, I mean, how long does this kind of a step take? I mean,
It depends. Sometimes it's 5 hours, sometimes it's 24 hours. There was one that was 4 days. So you like get it going and then maybe you go back and you start making a little bit more of your starting material so that you can, if it doesn't work, you're not just like wasting all this time. But it really just depends on how long the reaction will take.
So how do you know when you're done? How do you know?
You either follow a paper, and when they said they were done, you're done too. Or you can do this thing called TLC, which I've been doing some of recently, a lot of. And you can compare your starting material to what you have actually going on in your flask. And if it spots the exact same, then you know all you have is starting material. Whereas if like there's a spot that's the same as your starting material and a new spot, you can watch that spot that is the same as your starting material disappear over time and just produce your different compound that you're forming in your flask.
It seems like a lot of these changes you can't see except you put them through these fancy machines you were talking about. But then you said, were there any like physical changes you could see?
Oh yeah, yes. So I started out with a white solid, and then the second step I had a brown oil, and then after that I had another brown oil, and then they change in color. Sometimes they don't change in color. Sometimes you have a white solid to a white solid. But sometimes they'll turn into a tan solid. There's a lot of, there's stuff that you can look for in that aspect too.
Very cool, and you know what those different things mean.
Sometimes you know, sometimes you don't. Yes.
When you're talking about an energy barrier, are you talking about actually dissociating parts of the things or just increasing mobility?
When I'm talking about an energy barrier,
Heat, I think, right?
Yeah, so when you're heating things to overcome the energy barrier, what's the energy barrier?
so everything, molecules all have an energy barrier based off of what's going to be able to break that bond. So how much energy you would need to put into the system in order to break that apart. Because it's happy as is, right? But if you put more and more energy, you're giving more energy for it.
So you're trying to dissociate some of the components.
Yes.
Oh.
Yes.
I've actually got two chemistry questions.
Okay.
Can you go to the esterification slide?
Esterification.
It's like just first step. When you're making the meth.
Oh.
Yeah, that one. Were you actually mixing the thionyl chloride with methanol first and then throwing your carboxylic acid into it?
No, that all happened all at once. I threw phenylalanine and methanol in first, and then I put in, and it was in what was it in? I believe it was in dichlorometh. Well, I don't remember what it was in actually, but it was in a solvent, and I added everything in all at once. I added phenylalanine, and then the methanol, and then the thionyl chloride. And it was on an ice bath, and then I took it off of the ice bath because I didn't want it to react quite yet, and then I heated it up after that so that it would react with all of the thionyl chloride already in there and not as I was throwing the thionyl chloride in.
One more.
Okay.
You were putting the I on there so that you can make an azide and then ultimately a nitrene.
Yes.
Could you tell us what a nitrene is?
A nitrene is just I believe, a nitrene is just a nitrogen just bonded onto that, and it just has lone electrons. So it only is making that one bond to the whole ring, the nitrene. An azide, let's see. An azide is an N3, and then the nitrene would be just the N there. So it's really reactive.
Is it in with 2 lone pairs or 3 lone?
In with 1, 2, 3, 4, 5, 6. I believe it has a plus. I think it looks like that. A nitrate. Hold on. 5, 1, 2, 3, 4, 5, 6. That'd be minus sign. Yes. It's just a lone nitrogen. You took off the other 2 nitrogens and you left it with just one you guys can't see this over there, but you left it with just one nitrogen on it. I can't remember if it has, I believe it has a minus charge. It might have a -2 charge on it.
So the NMR you did was on hydrogen, right?
Yes, there was hydrogen. No, I didn't do a carbon NMR. I could have done a carbon NMR if I wanted more.
Carbon 13 all over the show there, right?
What?
You would have had a carbon 13 everywhere then, right?
Mm-hmm. Yes.
So how did you tell the difference? You just looked up the peaks?
There's specific peaks,
okay,
yes.
so you looked up what the numbers are.
Mm-hmm. And it's relatable. Like, it's been made before, so I could relate it to a specific peak that it was supposed to show up at. Yes.
So my understanding is that like they found that first molecule at the very beginning, but it had a short half-life, right?
The GLP-1?
Yeah.
Yes.
So is the point of this to like put iodine on it in order to slow down the half-life, make it last longer?
No, the iodine is just so you can attach it to that receptor. And then once it's attached to the receptor, then we can look at the amino acids on the receptor. That original molecule, GLP-1, that actually is formed in your body naturally. They found that first, but it only lasts for 2.5 minutes. So then they found TO632, which is very similar to that molecule, but we have to add the iodine in order to attach it onto that receptor. Yes.
When if you get this molecule to build it, do you send it off to like a biology lab?
Yeah, we send it off to Mayo Clinic, which does a lot of diabetes research, and then they actually are the ones that add it onto the receptor and chop it up into pieces and analyze the amino acids. I don't do that part. Yes.
Perhaps as a segue to next week's talk on RUs, could you maybe spend a few minutes telling our students about what an RU program was like? And, you know, as far as how long was it, you know, you want to talk about stipend, how was housing arrangements, you know, did you fly there, was housing paid for?
Yeah, so my RU was at Wellesley College, which is an all-women's college, and it's 30 minutes outside of Boston. And it was a stipend, so it was a 10-week-long program, and I got paid $6,000 to go out there. And then food wasn't paid for though, so I had to pay for that myself, and the dorms wasn't paid for, so I had to pay for that myself. So after everything, I made from the stipend $4,500, and that was awesome because now I can pay for school. And it was an awesome experience. It was so much fun. You're just in the lab 24/7. From the work day is supposed to be from 9 to 5, but I mean, if you start a reaction that's going to take 3 hours at 3 o'clock, you're not just going to be like, all right, well, goodbye. So sometimes you're in there later. Or if you start a reaction on Thursday and it's going to get done on Saturday, like you can't just keep it running till you get there on Monday. You have to go in and stop it on Saturday. But the weekends are all to you, so I did a lot of fun things on the weekends. I went to Boston a lot. I went to New York twice. I went to Cape Cod. That was fun. If you look at all my pictures, I was working, it was an all-women's college, so there was a lot of women. It was fun. We did a lot of things. As you can see, we played ping pong. There was a ping pong down in the basement. We went on trips and stuff. There was really supportive community since everybody there like wants to excel and exceed in science later in life. There's a lot of pre-med and then pre-grad school people there. Mine was really different. Normally when you go, it's people from all over the school or like all over the country. Mine was pretty much all Wellesley people except for like 5 outsiders. So that was a little bit different experience for me personally, but I really enjoyed it, and it just taught me a lot about what grad school would be like. Just science every day, going into the lab and working on things. And then there was a chemistry seminar every Tuesday, and then just like a seminar for the whole RU every Wednesday. That was lots of different, like that astromedical, somebody from Harvard actually came and gave a presentation on that, which I thought was really neat. And so you got all different types of talks all throughout every week. Yeah, I think that was everything. Oh, my before too. That was nice. Yeah.
Was there any beneficial results from your research for type 2 diabetes that you know of?
Okay, so this is like a really long ongoing project that I came in for 10 weeks to work on. There has been a lot. He's actually going to publish a paper, I think, in a year or so. That's like what he's looking to do. They've been sending different parts of people in the lab have been iodinating different places, and they're actually a lot further than I have because they work during the year. And so they've sent off a couple of those compounds to Mayo to analyze it, but they still haven't gotten the results yet. I've talked to them, not yet, but yeah. Yes.
So when you were iodinating that ring, you said it was going to add to the para position.
Yeah.
Why would it not add to the 1 or 6 positions? Also,
Okay, so the ortho positions. So we didn't really know that it was going to add. We thought exactly what you thought, and it just selectively iodinated there. It put it right on, only in that place.
Do you know why?
Why it did that? Not exactly. I don't exactly know why. It could have also iodinated in both of those places, and then it fell off when I closed the ring. So it could have been like a double whammy. It really just only left on in that one position. But that's just selectively what happened. Okay. It decided to go on in that place. Yes.
I think on one of your earlier slides with the interdisciplinary stuff, I think you forgot the mathematics.
I did forget the mathematics. I did forget the math. That's just because math is in everything. It just is all of that.
That was the heart in the middle.
That was the heart in the middle, is the math. There you go.
Do you have any other questions for our speaker? We got one over
Oh, yes.
Were there any other labs that Haynes Lab worked with frequently?
Nah, I mean, there was another organic lab that we would work with. Dora's lab. They were working on a very, very different project than us. We would share chemicals with them, but not necessarily. I know there's collaboration more during the year and stuff with ideas and such and like that, but not necessarily. There was a lot of other labs, a lot of other chemistry labs going on at the same time. There was an astrochemistry lab, which I thought was cool. I hung out with them a lot. There was physics labs. There was math, geology. It was a pretty big RAU program with a lot of different sciences. And we had a big poster conference at the end. That's me by myself with my poster. Oh, I'm wearing this outfit. Okay. Yeah, that's this morning. No big deal. All right. Do you have any more questions?